Up to now, we have only discussed about excitation from valence orbital, that is lead to UV visible spectroscopy. Now, if we give high energy radiation, it can knock out electrons from the core of the orbitals. Now, this core orbitals has a specific feature. These core orbitals are very tightly mined, so it is localized inside the near the nucleus, and so these core orbitals almost behave like atomic orbitals of that particular atom. So, these core orbitals are completely localized on the atom, so they are atom specific and they are sensitive to the surrounding chemical environment. So, although the UV visible spectroscopy gives me information about the overall electronic structure of the molecule, this core orbital spectroscopy or X-ray spectroscopy gives me the core orbital spectroscopy or X-ray spectroscopy gives me information with the atom specific details. It gives us information about the arrangement of the atom, what is the chemical environment, what is the distance. That is why X-ray absorption spectroscopy is so important. Now, depending upon so the X-ray absorption spectroscopy is essentially involves creation of some kind of a core electron process, and depending upon what kind of process it is, it can be considered into two separate property, and depending upon what kind of core hole is involved, it can lead to two kind of property. One is the creation of core hole, that is X-ray absorption and X-ray photoelectron spectroscopy, and the decay of the core hole in the X-ray emission spectroscopy or Auger electron spectroscopy. In the X-ray absorption spectroscopy, what happens is that one electron gets excited from the occupied core occupied orbital to the virtual orbital. In the case of XPS, what happens is that one electron gets ionized. So, you can think it in an alternate way as the electron getting excited from a core orbital and excited to a continuum where the electron gets vanished. So, this leads to X-ray photoelectron spectroscopy or XPS. The decay of the core hole actually leads to kind of spectroscopy, the X-ray emission spectroscopy. In the X-ray emission spectroscopy is actually a two-step process. In the first step, one electron is excited to the continuum, that is it gets ionized. Now, because there is a hole in the core of the molecule, this structure becomes unstable. So, what will happen is that one of the electrons from the valence orbital actually fall to the core, and depending upon from which valence orbital it leads, it will get to different kind of excited state, and because electron falls from the valence to the core, so there is excess energy get released, which get released in form of the radiation. In the case of Auger electron spectroscopy, what happens is that first one electron is ionized. So, one of the electrons from the valence orbital, so inner valence orbital falls to the core, and because of this excess energy knocks out another extra electron, ionize another extra electron. So, this is a double ionization process. So, this absorption spectroscopy, so these two different spectroscopies has different uses. So, X-ray absorption spectroscopy mostly used to study the metal centers, whereas the emission spectra gives you information about the ligands. Now, depending upon from which shell the excitation is happening, if it is from the happening for the first shell, it is called cage spectroscopy, second shell LH, third shell MH, like this it will go on. One of the important thing is to notice that to do this kind of X-ray spectroscopy, you need synchrotron radiation source, and the synchrotron radiation source are generally very huge facilities. There are quite a few around the world. There are a few in the Europe, North America, South America and Brazil, in Japan, Australia, there are many more, and each of them these are few facilities. This is the Riken one, the Japan, and you can see each of these facilities are quite big. It's almost big like a football field. But in the present day, you can also have tabletop instruments. This is an X-ray emission spectrometer. So, to have radiation source which are portable and easy to set up, these days become more and more common. So, X-ray spectroscopy is becoming more and more important in the present time. Now, this is an X-ray absorption spectra looks like. This picture is taken from this site. Now, in principle, X-ray absorption spectra are normal absorption spectra that are just taken in a spatial high energy wavelength range. Due to the high energy of the radiation employed, it's 7000 eV, core electrons are excited rather than the valence electron. There are two consequences. The method becomes element specific because the core level energies divide rather cleanly into regions that are specific for a given elements. So, the core orbital energies of oxygen will be completely different from carbon. So, if you have a compound containing carbon and oxygen, you can definitely tell which one is excited from carbon and which one is excited from oxygen. Second thing is that the wavelength of the radiation is so short that higher order terms in the expansion of light matter interaction becomes important, most noticeably the quadruple intensity. So, generally UV visible spectroscopy we are only bothered about the dipole intensity, but the only dipole intensity is not good enough in case of X-ray spectroscopy. You sometimes need to go to higher order things, which is also like quadruple intensity sometimes becomes important. And the X-ray absorption spectra can be generally divided into three regions. First is the pre-H. This region is called pre-H. That correspond to the transition of the core electrons into low-lying virtual orbital that leads to the bound state. So, this excitation from core to the virtual actually is a bound state processes. Then there is this rising age that correspond to the excitation to the high-lying state that are barely bound. So, these are like Rydbergs, and then there is an extended absorption. So, this region is called extended absorption fine structure region that correspond to the electrons being ejected from the absorber atoms and scattered to the neighbor atom. So, here the states, so the virtual orbitals where the electrons are get excited, they are so high energy that this kind of, so once the electron gets excited there, the states are not bound. So, the states get auto ionized and the additional electron gets scattered into the neighboring atoms, and that leads to extended absorption fine structure. With the simple TDDFT calculations described here, one can only focus the attention on the pre-H. Neither the rising edge nor the X-half regions are reasonably described to its standard electronic structure method, and no comparison should be attempted. In addition, these calculations are restricted to K edges, as the calculation of L edges is much more laborious and requires a detailed treatment of core hole spin orbit coupling. For K edge, you are actually exciting from the s orbital. So, L value is 0, so spin orbit coupling is not there. So, you do not have the problem of splitting of the peak due to spin orbit coupling. So, this is more straightforward. If you want to do L edge, you need to consider spin orbit coupling in your calculation. We will discuss about spin orbit coupling in later classes. The second thing is that this core orbital actually are very close to the nucleus. So, the electrons in this core orbitals moves in a much higher speed than rest of the molecules, rest of the orbitals. So, the electrons in this core orbital moves in a much faster speed than rest of the orbital. So, that leads to this high speed actually leads to what is called relativistic effect. Now, as we discussed before, because the L value is 0, so there is no spin orbit coupling in this case, but and sufficient to use scalar relativistic effect for this kind of calculation. We are going to discuss about relativistic effects also in the later classes. So, now this is how an input file will look like. So, Zora actually will give you the relativistic effect. I am using BP86 because I want to do the calculation fast, and for Zora you need to use this special Zora specific basis set, and you need to use this */j for the J basis set, and for the TDDFT input file, it's if I want to give enough number of roots, if I calculate all the possible roots, then of course I will get excitation from the X-ray also, from the core orbital also, which will give me X-ray spectroscopy. However, sometimes it's not a good idea to do that thing because you will calculate so many excited state, the cost will be very high, and if you are solving it via Davidson, high-lying excited state may not even converge. Hence, one can select the orbital window from where the excitation is happening. So, if I see the orbital window picture, there is first 2 0 0. So, that tells what is your donor orbital. So, your donor orbital only happens, the 0 0 is that it's only happened from the first orbital. So, my test system is TiCl4. So, this will be 1s orbital from Ti, and this -1 selects that all the virtuals are possible starting from LUMO to the last virtual, and I need the quadruple moment and I need the full semi-classical treatment, and I should calculate 25 roots. So, let us do this calculation. So, one important thing to notice here is that for each edge you will do it separately. So, titanium chloride has both the titanium cage and the chlorine cage, and one need to do them separately because the energy differences is so high that it does not make sense to calculate them together. Let me make a folder called XAS. TiCl4, let me write .INP. It may be a good idea to give the large print because I need to understand where from the excitation is happening. So, let me open the output file with Notepad. So, So, this is where the TFT calculation is done. So, if you see the orbital picture, it is interesting. So, first thing to notice is that this is the titanium orbital is first orbital is corresponding to titanium. It has an around energy around 4901 electron volt, whereas the 4 chlorine orbital is almost degenerate. So, whatever the small difference you see is due to the numerical issues. If you put very tight optimization, this orbital energy difference will go away. So, all the 4 chlorine will give you almost identical peaks. We will come into that. The first core orbital where I have did the excitation correspond to 4901 eV. Now, we will go to the spectra. So, before you do the property integral calculation, this calculates the electron quadrupole moment, magnetic quadrupole moment, electron octapole, electric octapole both in length and velocity calculation, and then it start doing the calculation. So, you see that all the energies are around 179, and after this is done, this is the electric dipole moment, and then this is the combined spectra with the quadrupole moment. So, if I now want to plot it using ChemCraft, first thing is to show the TD spectra. First see with electric dipole moment. So, then there is only one peak. If I do the broadening, because many of this has very small dipole moment, so this does not look good. We need to get the range little bit there, because all my energies are around 0.3. So, I need to change the frame. X-axis maybe 0.29, y-axis. So, this is how the spectra will look like with the broadening, and most of the peaks are actually concentrated along here. So, maybe we could have taken a even more. Actually, I should have done the energy values in EV versus intensity. Now, the pictures look fine, because the nanometer, the wavelength in nanometer becomes the problem that they are very closely spaced. So, you either use centimeter inverse or EV. The centimeter inverse is a proper spectroscopic scale. So, this is how the spectra looks like. So, this is if you use the all the TD spectrum. So, this is how the spectra looks like if you use all the electronic, magnetic and the quadrupole moment. If you just see electric dipole moment, the difference is actually quite small. But there are cases where including the quadrupole moments and the electron dipole moment can give you very small changes. So, this is about the TIH. Now, if I want to have the CLH, the thing is that this for the CLH we have seen that all the orbitals are quite close together. So, if I am optimizing from one or the optimizing from other, it should be same, but the problem is that their energy differences are so small that they will have contribution to each other. So, the core orbitals are generally local. Sorry, I did not show you the molecular orbitals, and I am exciting from the first molecular orbital. You can see now it has started having some kind of a density. Maybe I have to use another 0, not good enough. So, this is where from the excitation is happening. So, just see that this looks like an s orbital and so tightly bound. So, that is what the orbitals actually looks like. Maybe I should have, in addition to this, I should have did this 4 orbitals also, the chlorine orbitals, which are of very similar energy. Do not forget that. So, this is one chlorine orbital, this is here. So, problem is that in some of the cases they have contribution to each other, whereas from the energy values we know that they are supposed to be give me identical spectrum. So, how should I calculate? An easier way will be to localize the orbital space. I can do an unitary transformation of the orbital, so that my orbitals get localized. So, each of the core orbital actually is localized on the particular atom. So, I localize the orbital from 1 to 4, the chlorine atom, and the orbital window is now from 1 to 1, because just exciting from one of the chlorine atom should be fine, and my range of this one is -1 to 1. The fact that I am using a range of -1 to 1 you can see my starting orbital was 45 was my antibonding orbital, and the last orbital is 174. So, my starting orbital was 0 to 0 and 45 to 174. So, now in this case my occupied orbital, the donor space is from 1 to 4. I can use a localization of the orbital by using excess log 0 is equal to 1 to 4. So, whenever I am saying 0, it essentially means that I am talking about the alpha orbitals. For a closed shell molecule, the alpha and beta are same. So, this difference is nothing. So, we are going to now do this calculation. If I have an open shell molecule, I would have also did an beta kind of calculation. So, let me go to this one. TiCl4 ClH dot INP. So, this is where the localization has been done, and after the localization has been done, they are now on the individual atoms. You can go to the GBW file and plot it with the Orca plot and see that are they localized on the entire atom or not. So, here you see because of the chlorine age, the values are around 101. So, the calculation is done. So, I can of course plot this one using ChemCraft. And this is how the absorption spectra looks like. I will go to centimeter inverse scale, do the broadening. So, this is how the spectra will look like. Okay. So, in this course we have only talked about X-ray absorption spectra. It is possible to calculate by X-ray emission spectra or XPS spectra using ORCA. I have not discussed anything about it. If you are interested in them, you should go and check the ORCA manual. Second important thing is that in this course we have only talked about excitation from closed shell compound, and that is when you can specifically tell that the multiplicity of the target state is singlet or triplet. Also, for that case we have also not considered the spin orbit coupling. So, the singlet to triplet transition is considered to be forbidden. If I start with an open shell reference, if the standard case, if I use unrestricted orbital, it is not very straightforward to say the target state multiplicity, what will be its target state multiplicity. Although there is a formalism in ORCA which is called restricted open cell CIS, which allows you to specifically find out excited state of particular multiplicities even starting with an open shell reference. There are other ways to calculate excited state than what we have discussed. One is delta SCF, where you can converge the SCF solution to an excited state that we have not discussed. You can find it in the ORCA manual. You can use the multi-reference based methods like a CAS SCF or CAS PT2 to calculate excited state that we have not discussed, but that we are going to discuss in the coming classes. For everything else, you should find the ORCA manual. So, in this course, we have discussed how the excited states are calculated, what kind of methods you should use, what are the available methods and their pitfalls. We have discussed that the DFT can have a problem with charge transfer excited state. So, you need functionals which are long range corrected like KMB3LIP to calculate proper charge transfer excited states. And we have discussed the excited state can be of three kinds: valence, Rydberg and charge transfer. For Rydberg, you need diffuse basis sets. For charge transfer, you have to be very careful because DFT methods are not very good in describing. We have seen how to optimize geometries with the excited state methods, and we have seen how to calculate X-ray spectroscopy parameter from DFT calculation. Up to now, whatever calculations we have done is all in the gas phase, but most of the real life processes actually takes place in the presence of an environment, and often that environment is a solvent. So, in the next week, we are going to see how to incorporate solvent effect in computational quantum chemistry calculation. See you next week.